Peace be upon you and God's mercy and blessings. Now we want to talk about the transformer differential protection system and how it is applied in numerical relays. Let's take an example. If I have a DYN3 transformer and I chose DYN3 because I want to learn several things from it. If I want to apply the differential protection system, I need two current transformers. One should be on the high voltage side, which is the delta side, and the other should be on the low voltage side, which is the star side, and they will be installed in this manner. Of course, if we refer back to the lectures on protection systems, and I will show you my link now, we will know that my protected zone is located or formed from where the CTs are placed. Therefore, all this red area is my protected zone. Naturally, there is a difference between the term protected zone and protected object. The protected zone can contain more than one object. As we can see, for example, I have here a part of the GIS, a circuit breaker, a cable, and a transformer. On the other side, I also have a cable, a breaker, and a part of the GIS or switchgear, depending on the case. Therefore, there can be more than one protected object within my protected zone. Very good. Also, as I can see, my CT has subtractive polarity, and the CT star point must be towards the protected object. Of course, if it is not present in the protected object, there are solutions to bring it back again in the protection system. Let's see together if I have a three-phase CT, how it is connected to the numerical relay. So, how will they be connected to my numerical relay? Initially, we take the terminals of the CT that face towards the protected zone, or the protected object, and form the neutral point from them, which becomes the CT star point, and it is grounded. Additionally, we take the external terminals of the CT and connect them to the dot point in the relay, or the entry point in the relay. In this case, the priority setting in the relay will be towards line, or depending on the manufacturer, there might be terms like standard or towards object. Very nice. Well, let's take an example with numbers. If I told you that I have a step-down transformer and the transformer S60 MVA, and the transformer is 60 megavolt amperes, the voltage on the high side is 132 kilovolts and on the low side is 13.8 kilovolts. Therefore, with a simple calculation, the current on the high side equals S over the square root of 3V, which will equal 262.43. The same applies to the low side, which will equal 2510.22. The only difference is that it is S over the square root of 3V of the low voltage side. I will use a CT ratio on the high side of 300 to 1 and a CT ratio on the low side of 3000 to 1. Now, if I tell you that this transformer during normal loading conditions means the transformer is operating very normally at full load, and therefore the currents will be moving in this direction. So the currents on the secondary side, as a result of the subtractability of the CT, will be moving in the opposite direction. Currents on the high voltage side equal 262.43 in a three-phase, even if they are not phased. And of course, they have angles of 0, 120, plus 120, or 0, 240, plus 120. As for the low voltage side, it will equal 2510.22 on the three-phase angle. And regarding the angle, let's see together the angle, the angle, the angle, the angle, the angle, the angle, the angle. Now, you have the current here. It went out from one point and went to point D and therefore, for me, it will be an angle with 0 degrees with respect to the angle of 120 for the yellow phase and an angle of 120 for the blue phase. Okay? Towards the low voltage side, what is the situation for me? The idea is quite simply, as we see, that the current here is reversed, meaning it went out from the dot point, so it approximates an angle of 180 degrees. Also, I have my vector group here. You have 333 at 90, and we know now that the star side will find the delta side at an angle of 90, so 180 minus 90 gives you plus 90 degrees. Of course, you don't need to calculate the other two phases again. You simply take the 90, subtract 120 from it, and take the 90, add 120 to it, or subtract 240 from it. This way, you've obtained the angles of the other phases. For the secondary side of the current transformer, you will divide it by 300 to 1, divide it by 3000, divide it by 3000, and divide it by 300 to 1. 0.87473 phase, and you divide this value by 3000, resulting in 0.8367 also on the three phases with the same. Alright, Let's look at the stability condition now. We are now dealing with the numerical relay pilot as we learned in previous lectures. This pilot deals with the per unit value. How? The relay reads the measured pilot in amps and divides it by the nominal pilot to convert it to per unit, and then multiplies it by the compensation matrix to do matching for the vector group and the inode elimination. Matching for the vector group and the inode elimination topic, the nominal is equal to the transformer in kilovolt amperes divided by the square root of 3 in kilovolts multiplied by the side ratio. Whether it's the high voltage side or the low voltage side in kilovolts multiplied by the side you are on, and consequently the result will come out here in amperes. Let's look at the compensation matrix. On the high voltage side, we use compensation matrix number 0. You gave the transformer DIN3, so the D is D0. And matrix number 0 is a matrix where when you multiply any number, it appears exactly as it is, as if you multiplied by 1. There, exactly. As for matrix number 3, how do I obtain it? There is a method I will tell you about in this lecture, and in the next lecture, I will discuss how to discover or calculate the matrix. The traditional method is that we have the 3 by 3 matrix, which is the general matrix from which you can derive any matrix you want. By substituting k with the number in vector group 3, we substitute k with the number 3, which becomes cosine 3 times 30, 90 cosine 3 plus 4, 3 times 3, 7 times 30, 90, and so on. Consequently, I will eventually discover that this is the overall result for matrix number 3, which is excellent. Let's observe how the planes will appear to the high voltage side. The planes will read the abstract current and divide it by I nominal to the high voltage side, which is the same as the bird's cup, because we said that the transformer is fully loaded. The per unit is 100% or 1. 747. This will be divided on the side, which is also the same as the pilot's cup, because we said we try to bear the load. So naturally you understand that it is considered, or 1 is considered 1. And what number does it multiply in the matrix? In the matrix it's number 0, and therefore the total result will be 1 over 3 phases at an angle of 0.240.120. So what is the unit of measurement here? The unit of measurement here is per unit because I have already divided it from the base. Okay, on the low voltage side, I will take my matrix, which is matrix number 3, and multiply it by the current value of this measurement divided by the nominal. I will find that the total result is 111, and my angles are 180, 60, and negative 60. Now we know what the differential equals, right? It equals the vectorial summation of the transformer currents, which is the directional sum of the high voltage side current and the low voltage side current. And low voltage side current, in this case, what will the differential value be? It will equal the high voltage side current, 111, at an angle of 0, 42, 120 plus 111 at an angle of 180, 60, 60. If you draw it even in the vector diagram, you will notice that the current on the high voltage side and the low voltage side for all phases are 180 degrees out of phase with each other. Therefore, the total result will equal 0, which means you have reached the stability condition, meaning during normal operation we found that we are in the elastability stage. Let's take a look at a simple part. To understand the topic more deeply, and grasp the idea very well. Suppose I told you that I have an external single phase to ground fault on phase A, as we can see here. Is there anything like what we see here? I should place it externally, and the relay should not make a mistake and trip incorrectly. Very good. Now this is a single phase fault on the red phase, meaning the current will be drawn here from the red phase, as you saw. Normally, the flux drawn from the red phase here will be countered by the red phase on the delta side. Correct, so the current will be drawn in this manner. Consequently, for the current to flow through this winding in the transformer on the delta side, it will flow through the external cables from phase B of the transformer and return from phase C. Now, regarding the CTs on the star side, I will find that the CT of the red phase is the one that reads the current. We will find visa yellow, visa blue, visa B, visa C, and visa A. You have not read the pilot at all. And similarly, phase A did not read any current at all. The relay must handle this issue that we will discuss, which is the topic of vector group compensation and inode elimination. Was this topic correct? Alright, let's see how the relay deals with this issue so we can calculate it numerically. I mentioned to you that in a single phase to ground fault, the voltage drop value is twice the fault current value of the transformer. As an example, very nice. The voltage current of the transformer is quite good. So I will tell you regarding the low voltage side, of course I have matrix number 3 as it is, and the current is twice the full load current, which is 2 times 0.8367 divided by the nominal value. Nice. Okay. And what is its angle as a result of the current? Alright, it's also external in this direction, so it will come to you in this direction here, meaning it is moving out from your dot point and entering here towards the star point. And therefore, its angle is 180 degrees. So, where is the effect of the vector job, which is an angle of negative 90? It's not present. You have a single phase, right? And thus, this is the final result. If you multiply this matrix by this matrix, you will find this as the final result. Wow, now here, the fault is on phase A, and despite that, I found here 0 in A, and phases B and C are the ones that have currents. Pay attention now. If your understanding starts to see the matter differently, then I immediately understood it, as if it is creating the currents first, just on the yellow phase, and the blue phase, because it knows that if you take the number 1 and multiply it by the currents that are already red from the yellow phase, and the blue phase, it will still result in the yellow phase and the blue phase. But here, there is a small trick. What is it? Of course, the current passes through the star, so the current passes through the delta, but we need to be aware of something here for you. The transformer current this time is the same as the phase current, which means I have to divide the current by the square root of 3. 3, alright, okay then. Therefore, we observed the specific currents for the differential current. The differential current will equal the sum of the two currents in their respective directions, so I will take the star current plus the delta current. If you take both together in the manner you see, you will find in the end that the differential quantity is 0, and thus you achieve a stability condition. From this, I observed that even if a single phase to ground fault occurs on the star side and drags the system, it coincides with the delta. So, a phase or outgoing phase that you manage to overcome, that's number 1. Number 2, the phase in the star, and the outgoing phases are completely different from its type, or the phases in the delta are completely different from the type of phase in the star. This means that on the other side it's yellow-blue, and despite that, also, it can handle it. You can refer back to the second lecture where we saw the matching city and how we reached the vector group and how to deal with it in an electromechanical relay. You can see how it can do this through the compensation matrix.